Okay, so in this section, we're going to talk about everything dealing with radicals, right? So you're familiar with square roots, I suspect, but maybe you're not as familiar with cube roots and fourth roots, or how you add, subtract, multiply, and divide roots. And so we're going to review some of that in this lesson, just so that you're familiar with them as they come up later on in the course. All right, so the first thing is kind of a notation. I will say that a is the nth root of b if you can raise a to the nth power and get b back. So for instance, we would say that -3 is a fourth root of 81 because you can raise -3 to the fourth power and get 81 back. Okay? Similarly here, we'll say of what number is -5 a third root? Well, to answer that, you'd raise -5 to the third power to get -125. And so -5 is a third root of that number. Okay. For this one, when you look at 49, technically there are two square roots of 49. You only think of the positive one, I suspect, because that's ingrained in you, is to think that square roots are always positive. But by our definition, you can square both -7 and 7 and get 49 back. And so technically those are both square roots of 49. What we would say, though, in this instance is that 7 is the principal square root. It's the positive one. And that will be something that we do for any even root. So any like second square roots, fourth roots, sixth roots, any of that, the principal one will be the positive one. In terms of notation, the nth root of b is just written with a square root sign with an n as an index. So if I wanted to simplify this one, for instance, the fourth root of 625, you have to ask yourself what number or numbers can be raised to the fourth power and get 625 back. And we know that 5 and -5 both make that true. But remember, we want the principal root when it's even, so only take the positive one in this case, right? So using this notation, it's understood that you're only going to want the principal root. That's true for any even index. If, however, the index is odd, the principal root may not be positive, right? There might not be any number that you can raise to that index and get a positive number out. Like for instance here, the only number you can raise to the fifth power and get -32 back is in fact -2. And so -2 is the fifth root of -32. Don't make the mistake here and get rid of the minus, right? That's part of the actual fifth root. All right, so some special situations here that often arise when you're trying to simplify radicals. Right? So if I take the nth root of something to the nth power, right? So let's look at just an example just to kind of conjecture what ought to happen here. We know if I took the square root of 9 squared, well, we know 9 squared is 81, and we already know the square root of 81 is 9, right? So that's not alarming. If you look at this guy, the fourth root of -2 to the fourth, remember you're going to actually raise the minus to the fourth power here, and so -2 to the fourth is 16. What number can you raise to the fourth power to get 16 back? Again, we're assuming this is a principal root because the index is even. That number is 2. If I took the fifth root of 2 to the fifth, remember 2 to the fifth is really 32. What number can you raise to the fifth to get 32 back? 2. So all of these examples, if you look at the even guys, so even index ones here, you never got a negative on the as a result, even though the thing being raised to the index inside might have been negative, right? But they do bear relation to the thing being raised to the power every time. Here 9 gave you this guy, -2 became 2. So it's almost as though you get the absolute value of the thing being raised to the power inside, if in fact it's an even root. That's what I'm saying here. But in the case when it was an odd root, an odd indexed root, the negative remained, right? And so we don't actually have an absolute value on this case. Go ahead and try this example. Right? You want to think of this, rewrite using the exponent rules, rewrite 3 to the 12th as something to the fourth power so that we can then use this result. See what you get. All right, so what you want to notice is that 3 to the 12th, you can rewrite that as 3 cubed to the 4th, because remember, if you have a power to a power, you're going to multiply those powers. And so the 4th root of 3 to the 12th is equivalent to the 4th root of 3 cubed to the 4th. But now we have the 4th root of something to the 4th. That root is going to give you that something that is being raised to the 4th. If there had been a negative here, you would have gotten rid of it because this index is even. But there's not, so it just became 3 cubed. 3 cubed, remember, is 3 times 3 times 3. Don't multiply the base and the exponent, right? And you get 27 back. All right. In terms of the your turn, you have the 5th root of 5 to the 15, right? So if you want to rewrite 5 to the 15 as something to the 5th power, you have 5 cubed to the 5th inside, an odd index root of something to that same power, you just get that thing back. And so you get 5 cubed or 125. All right. In terms of notation, again, this is just notation, but using it actually helps us to use the exponent rules that we already know exist, right? And so that's actually quite useful. The nth root of b, we're going to rewrite that as b to the fractional power 1 over n. Right, so let's actually simplify these expressions with that in mind. So let's first look at the first one. Right, minus 27 to the 1/3. Well, that's just notation for the cube root of minus 27. But you can rewrite minus 27 as minus 3 to the 3rd power. We have an odd index root of that thing to the same power, so you're just going to get that minus 3 back. Again, remember, if it's an odd index, you do not get rid of that negative if it happens to be there. Okay, let's look at the next one. 25 to the 1/5 really means the square root of 25, right? The square root of 25 is really 5 squared. It's an even indexed root, so you just get that 5 back. All right. And then for the final one, 64 to the 1/6, that means the 6th root of 64. What number can you raise to the 6th power to get 64? Well, technically 2 or minus 2, but remember in the end here, you want the principal root, so that negative isn't going to matter. And so just use 2 to the 6th. 6th root of 2 to the 6th is 2. All right, so let's look at these. We talked about fractional exponents where the numerator was always 1. Well, now what if it isn't? Right, so what does it mean to talk about 49 to the 3/2? Let's actually look at that. Right, well, we know that 3/2, that exponent can be rewritten as 1/2 times 3, right? And we also have in the back of our mind, we have those exponent rules that we talked about in the previous section. So let's look at this. 49 to the 3/2, well, is equal to this guy, because you know that if you take a power to a power, you just multiply the powers. And so if I rewrite this quantity in this way, I can do one step at a time. I can take 49 to the 1/2, that gives us root 49, all to the 3rd at the end. But root 49, the square root of 49 is just 7, right? And so the inside here is just 7. 7 cubed is 343. So the way to think about fractional exponents like that is to write them as a product where the fractional part has a 1 in the numerator and then the other part is just an integer. We can then use our exponent rules to be able to simplify easily. The only extra hitch here is now we have a negative. And remember that negative is just a notation that tells us to take whatever is being raised to that negative power to the opposite place in a fraction. And so what our first step here is going to be is to take this 81 to the minus 3/4 down to the bottom. Right? Once it's down below, realize that 3/4 can be written as 1/4 times 3, which we did. Same exact thing. 81 to a power, you'd multiply those powers. And so this really does mean the same thing as that. Nice thing here, though, I can rewrite the inside as the 4th root of 81. And I know that if I raise 3 to the 4th power, I get 81 back. And so in the bottom, we have 1 over that thing cubed, but that quantity inside the parentheses is equal to 3. 1 over 3 cubed is 1 over 27. All right, you can go ahead and try this your turn on your own. Do the exact same thing. Rewrite 3/5 as 3 times 1/5 and proceed. You can check that on your own later on. Okay, now let's actually see what happens if you start putting in variables. Right, remember variables really are just taking the place of numbers. And so we have to be careful with how we simplify in the end, especially when we're talking about even index roots, because we know that we cannot get a negative as an output of one of those, because the assumption is that we're looking only at principal roots. All right, and so here is this guy. So let's rewrite, we're taking a square root of something, so we want to write the inside as something squared. Using our exponent rules, that's just x to the 5th squared. So technically now we're taking the square root of that thing squared. The tendency to think is that this would just be x to the 5th. Problem is, what if x were negative? Right? If x were -2, -2 to the 5th power really is -32. So we know that the square root of something can't be -32 just by our convention. And so to avoid that issue, I'm going to put absolute values around the thing being raised to that 2nd power. All right, I'm going to just briefly go through these. So again, I gather all these rules together just so you have them all in one place, right? We've already talked about the first one, and the second one, technically, we did as an example above. But here for 3 and 4, what it tells you is that the square root of a product or a quotient can be written as the product or the quotient of the square roots, right? And so you can break up products and quotients. You cannot break up sums or differences for the same reason that you couldn't square a binomial by squaring the 2 terms and adding them, right? That's not how exponents behave. And number 5 tells you that this is basically used to get rid of square roots in a denominator, right? So in high school, they probably harped on, you can't have a radical in the bottom. Technically you can, it's not gonna, blow up if you have it down there. The reasoning behind having radicals at the bottom or not having them goes way back to when people used slide rules, believe it or not, in the 50s. There you couldn't divide by a radical. It just wasn't physically possible on that machinery. And so you had to do this. But now it's a good way at least to practice using radicals and their properties. So we're going to adhere to that rule as well. To get rid of a radical in the bottom, you just multiply top and bottom by that radical. Remember? So if you do that, you're just multiplying by 1. To multiply fractions, you multiply across the top and the bottom. So the top just becomes radical A. And here, remember, radical A is really a to the 1/5 power. So if you, a to the 1/2 power. And so if you have a to the half times a to the half, if you multiply powers of the same base, you add the powers. A half plus a half is 1. And so you get a to the 1st power down below. Right? That process is called rationalizing the denominator. All right. 6 and 7 are kind of natural sort of things, but they'll help you later on when you're trying to solve equations by taking a square root of both sides. Right? So if you have 2 quantities that you know to be equal, and those quantities are non-negative, you can take the square root of both of them, and you get the same thing back. So it preserves the equality in that case. Furthermore, it preserves the inequality, right? So if you have 2 positive numbers, one less than another, if you take square roots across that inequality, it's maintained. All right. So here, I'm not going to harp much on this. You really just have to practice this really to get good at it. But I'm going to talk you through a couple of them just to kind of show you how those properties work, and then I'll have you work through your turns on your own. All right, so for the first one, the question is, how do you compute the square root of 48? Or how do you simplify that? So here, you want to rewrite the inside, if you're able to, as a product of two numbers where one of them, or one or both, is easy to take the square root of. Right? So 48 is 3 times 16, right? So I know that these are equal, but we have a square root of a product. We know that's the product of the square roots. And so though you can't simplify radical 3 anymore because 3 is prime, you do know that radical 16 is 4. Right? And so this simplifies to radical 3 times 4. And whenever you have that, whenever you have a number outside of a radical times a radical, it's customary to put the number in front only because you don't want to misinterpret the fact that it's not under the radical sign. That's the only reason for doing that. But we know we can do it because multiplication is commutative. You can change the order. Okay, for this one, you're going to go in reverse. The cube root of 9 and the cube root of -3, neither of those can be simplified by itself. But we have a product of roots with the same index. I can rewrite that as a cube root of the product of the radicands, right? So in other words, I'm using that multiplication property backwards. The good thing about doing that here is that if I multiply 9 and -3, I get -27 back. And here you do know that you can compute the cube root of -27 easily because -27 is -3 to the third power. Okay? Cube root of something to the third is just that something. All right, and I'll let you read through these two as well, All right, let me look at number 6, just because I want to make sure you realize. Here you have a square root of a sum of pieces. You cannot distribute the square root to each of those pieces independently. That's not an allowable operation. What you can do, however, is observe that the radicand can be written as x plus 2 quantity squared. Right? The minute you have that, the square root of something squared is technically the absolute value of the thing being squared. Again, remember that x represents a real number, and if x were -5, you don't want the output here to be -3. You want it to be +3. All right, so go ahead. These are just more examples of this. I'll have you read through those. One quick note, though, as you do this. Here, notice that on all of these, the radical went away completely, except for right there. Here, the idea of simplifying these terms, what do you mean by it, right? I mean, what you want to do, you'd like to kill off the radical completely, but you can't necessarily do that, right? And so what the idea is to get rid of as much underneath the radical sign as you possibly can, meaning that you can't take out any more powers, you can't take out any more numbers or factors inside the radical, right? So let's actually look at it rather than having you do it by your own. So for cube root of x to the 7th, what we do know is you could take out anything that's being raised to the third power, right? We know that. And so what I'm going to do is write x to the 7th as x cubed times x cubed times x, right? We know that's true because if you multiply powers with the same base, you add the exponents, right? So that's certainly a true statement. All right, so if I do that, I know I can rewrite the cube root of x to the 7th in this way, but we have that product rule, right? Cube root of a product is the product of the cube roots, so I can rewrite those in that way. But on each of these first two pieces, I'm taking the cube root of something cubed. That just gives you that something in the end. Don't need absolute values here because that's an odd index. So in the end here, what you get is an x times an x. Cube root of x can't be further simplified. There's no hidden third powers in there, right? So we just leave it as is, but we could multiply those x's together to get x squared. And so in the end, what this radical expression simplifies to is just x squared times the cube root of x. Okay. I'll let you read number 2 on your own. And if the your turn here, these emulate basically the previous examples. So I will let you do those. I'll show you the answers on screen real quick, just so you can actually stop the video, but I'll let you look at those on your own. All right. let's go on to adding and subtracting. Now that we know how to simplify radicals, let's go on to adding and subtracting, multiplying, and dividing them. Basically, you want to think of the radical part as just like you would a variable part in an algebraic expression, right? So if this were 2x plus 5x, what you would have done is simply notice that the x's were identically the same. You would have added the 2 and the 5 and written that as 7x. Absolutely no different here. If two expressions have exactly the same radical part, you can add the numbers in front of them as they were coefficients, keeping that radical part the same. And so that becomes 2 plus 5 times the square root of 3, which is just 7 root 3. All right. For this one, let's just talk through it. You'll notice here, none of those radicals are the same. So your inclination would be to say, well, you can't combine them, that's it, leave it alone. Not necessarily true. You can simplify each of those like we did earlier, and then once you simplify them, you can see if they have the same radical part. So let me just show you what happens if you do. This is the kind of the grunt work behind simplifying them, but you'll notice that in each case, there's only a 3 left underneath the radical sign after you simplified each of those independently. So in fact, these 3 terms are all constants times a radical 3, so they are like terms. You could yank that radical 3 out and just add the coefficients. Okay. All right, so here, for example 3, notice these are already simplified, right? You don't have to further simplify the radicands, but while the first and the third terms have the same radical part, the middle one does not. And so all that means is you can group the first and last terms together like I have here and add their coefficients, but you simply cannot combine the 4 radical 5 into it. There's no way to further simplify this result. And so that's considered to be simplified. All right. When dealing with radicals of fractions, remember we have that other property. Radical of a quotient is the quotient of radicals. And so that might be helpful here to actually use that before you try to simplify. Give that a go and see what happens. Okay, let's look at it. So the very first thing I do is I take the radical of a quotient and apply that is the fact that it's equal to the quotient of the radicals in each case. And then I go ahead and simplify each of those 4 radicals in turn. Now you have 2 fractions being added, but they do not have the same denominator. And so you have to get a common denominator, which is 15, 3 times 5. And so to convert these guys to equivalent fractions with the same denominator, I'm going to multiply the first one in top and bottom by 3, the second one by 5, and then they both have a denominator of 15. If you're multiplying here, you don't multiply both the 3 and the radical 2 times the 3. You just multiply the number out in front by it. And so we have 3 times 3, which is 9 radical 2, 5 times 4 times radical 2, which is 20 radical 2. And then you have like terms here. They have the same exact radical part. So I can add the numbers in front to get 29 radical 2. All right, and this I already mentioned, right? You cannot distribute a radical through a sum like that, right? That's just like the fact that you can't FOIL or you can't square a binomial by squaring just each number and adding them up. Okay, so just be aware of that. It's a natural mistake that people make all the time. All right, so what if I want to multiply expressions involving radicals, right? So I have a binomial times a binomial. It just so happens now that we have radicals in there instead of just variables. Same exact process works, right? This is product of 2 binomials, just FOIL it out, multiply this 5 times both terms, this minus radical 3 times both terms, and add the results, okay? So if I do that, you're going to get a sum of 4 terms, right? That's 35. These 2 can't be further simplified, but you can add them because they're the same, like they have the same radical part. So I'm going to add the 5 and the negative 7 to get minus 2 root 3. And here, you don't want to leave that like this. We know the square root of something squared is the absolute value of that something. Well, that's 3 in this case. This minus sign does not go away. You're subtracting that from something, right? And so it just stays as a minus 3. You can combine the 35 and the minus 3 into 32, and so this is your end result. Right? So go ahead and try this example. I'll let you try it, and then you can check yourself here in a moment. Okay, so go ahead and you can take a look at that. It's no different than the other one, just a little more simplification perhaps. Same exact thing for this your turn. Go ahead and try this, and I want to talk about it when you're done. All right, so let's look at this. So instead of actually applying those properties, what you want to do here is see how much you can cancel on top and bottom first, and then apply the radical properties, right? So there are often different approaches you can take that make your life slightly easier. And that's particularly true in this instance. Notice I can rewrite 36 as 18 times 2, and I can write 30 as 5 times 6. Right? So if I do that here, the 18s go. Furthermore, the square root of a product is the product of the square roots, so I can rewrite the denominator as root 5 times root 6, and lo and behold, those radical 5s go. Right? And so what I'm left with at this point is 2 over root 6, which is perfectly fine. That's equivalent to what we had at the beginning. Problem is, it's not one of the choices. And so what I have to do instead now is I need to rationalize this. Remember, to get rid of a radical on the bottom, I'm going to multiply top and bottom by that radical, namely radical 6. And so if I do that, that's what's going on in this step here, I get 2 root 6 in the top. But if I multiply root 6 times root 6, I just get 6 back. Finally, get rid of a 2 into both the top and the bottom. That gives you root 6 over 3. And so your answer is E in this case. Okay, here it's another good one. Go ahead and try this and see what happens. All right, so be careful. Again, this is what I keep saying. Do not square the radical 2 and square the radical 27 and subtract. That doing so would give you A, but that's not the correct answer. You need to FOIL this, first, outer, inner, last. Right? And so if you do that and you keep careful of the bookkeeping, you'll eventually get D as your answer. But take a look at that just to make sure that you got each of those steps correct. Okay, so this one, this comes up every now and then, especially in Calc 1 when you're talking about limits. There's a particular trick that you like to use to get rid of radicals in the bottom. So I want to make sure that we can do that. We've already talked about an example like this guy, right? You just multiply top and bottom by root 3, it gets rid of the radical in the bottom. Fine. But this one's a little bit trickier. Okay, let's look at that one. All right. The inclination here, the thought would be to simplify this. Let's multiply both top and bottom by the denominator, right? Because that's what we did over here. You multiply by root 3 over root 3. So here, the natural instinct will be to multiply by 2 minus root 5 over 2 minus root 5. The problem is, if you do that, if you multiply 2 minus root 5 times itself, right here, oops, well, I don't actually show that particular guess. But if you multiply 2 minus root 5 times itself, you're going to get a root 5 that remains. Okay? Furthermore, if you just multiplied it by the radical, like what I'm suggesting here, it gets rid of the radical 5 on this side. I agree with that, but you produce a radical on the first term, right? So it's not going to help out. The trick is to multiply top and bottom by what's called the conjugate of the radical term, right? So in other words, the conjugate is the same exact expression, but with the opposite sign. If I were to multiply 2 minus root 5 by this guy, notice I get 2 times 2, which is 2 squared. I do square the radical 5, but the inside term and the outside term are the same with opposite sign. They cancel. Why is that good? Well, now I get a 4 from here, and I'm getting rid of this radical because I'm squaring it. Right? So you get 4 minus 5, which is negative 1. there's no radical. Okay, and so if you look at our original quotient, this guy, I'm going to multiply top and bottom. Remember, you can't just multiply the bottom by it, right? You have to multiply a fraction by 1 so you don't change the value. If I do that, the top just leave as is for the moment. If I multiply out the bottom, I get -1. If I distribute that 7 through, I get 14 plus 7 root 5. Now, if you have over -1, you can just put that negative out in front, right? So you get this in the end. All right, go ahead and give this a go and see what happens. Right, you want to get rid of the radical in the bottom in each case. See what happens. Okay, so let's look at the first one. I know I'm going to multiply by both top and bottom by the conjugate of the bottom. Well, the conjugate is the same thing as it's here with the opposite sign. So I multiply by 1 minus root 3 over itself. If I multiply this out, remember this is a difference of squares in reverse. I'm going to get 1 squared minus root 3 squared, which eventually gives you -2, and then multiply that 4 through both terms in the top. If you do that, actually before you do that, you can get rid of the -2 at the bottom into that 4, right? And so you can do this instead. You can get rid of the -2 into the 4 to get -2, and then distribute that -2 through. Okay. Had you already distributed the 4 through, you'd have to then yank it back out. So you'd have to have undid what you did. But in any case, the most important part here is the so-called rationalization. For this guy, you're going to get rid of the radical in the bottom by multiplying by its conjugate. The fact that there are 2 radicals is not worrisome, right? So you're just going to multiply by the same expression, but with the opposite operation, right? That'll still give you a difference of squares down below. So you get a radical 2 squared minus a radical 5 squared. And so both radicals are being demolished, right? If you simplify the top, remember to multiply that radical 2 through both terms. That gives you that product and that product. But radical 2 times radical 2 is 2. A product of radicals is the radical of the product. So this is radical 10 over -3. And you can just leave that like that. Okay, the last topic in this section is on complex numbers, right? And so everyone has probably heard of, at least in passing, the number I, right? And what you think of if you've heard of it is that I is the square root of -1. I hate actually thinking of it that way because we already told you can't take the square root of a negative number. Yet here we are defining something that does just that. So technically, we define a number I to be a number for which if you square it, you get -1 back. Right? So I don't actually write the notation I equals radical -1, though you will see that, which is fine. All right, so a complex number technically can be written as a sum of 2 pieces, namely a real piece and a piece that's multiplied by I. Right? And so some examples are 2 plus 3i and 16 minus 7i. Those are true complex numbers in the sense that they're most general. But every real number technically is complex because you can take b to be 0. And this guy is called purely imaginary because there's no real part. The a is 0. All right, so the question now really is, how do you simplify, or how do you work arithmetically with complex numbers? And the answer is, well, no different than you did with radicals, because you can think of I as radical -1, technically. And so every rule that we just talked about applies in this setting. All right, so let's look at these. For radical -25, what you want to do is yank the I out if it happens to be there, right? And so if I'm taking the square root of -25, well, that's 25 times -1. Square root of a product is the product of square roots. I can write that as the square root of 5 squared, or 25, times I squared. Remember, because I squared is -1. And radical 5 squared is 5, radical I squared is I. And so you just get the 5i in this case. For this guy here, I'm going to distribute the I through. And so I get 2i minus I squared. But remember, I squared is -1. And so I substitute in -1 for I squared. And that gives you 2i plus 1. And it's customary to write the real part first. You don't have to, but that's how you'll see it done. All right. And then finally here, Again, with the foiling business, you don't square the 1 and square the 5i and be done with it. You have to literally multiply this out. And so I have first, outer, inner, last. I have 1 times 1, which is 1 squared. Both the inner and the outer terms are 5i, and then 5i times 5i is 25i squared. But remember, when you square I, you get -1 back. And so I can add those constants to get minus 24 plus 10i. All right, you can go ahead and try these. They are basically identical in structure to the previous ones, and then I'll scroll up so you can actually check your answers once you've done that. Okay, so there are the answers. Make sure you go through and just check, but the steps are identical to what we just did. Okay, so again, there's a lot going on in this section, but hopefully most of it is kind of recall at this point. So go ahead, try the video supplements if you need to. If not, leap in here and see how it goes. Let me know.